with a definition of a planar graph which is inherently visual, the idea that it can be drawn on a plane, on a sheet of paper, without taking your pen off and without crossing any edges. The actual proof that a graph is planar, the easiest way to prove it is literally to draw it. Particularly for relatively small, finite graphs, it might be a challenge. You might have a few failed attempts before you get to a correct attempt, but proving a graph is planar, the easiest way to do it is generally to draw it. Proving the graph is not planar is often more of a challenge, because drawing the graph correctly and crossing a line over proves that you have not represented it in a planar way, but it doesn't prove that there isn't a planar representation that you've just missed. So proving the existence of something just involves having that form. Proving the non-existence is a bit harder. Because if I consider a simple graph here, which is 4 nodes, and indeed it's the complete graph with 4 nodes. So the nodes here are A, B, C, and D, and every node shares an edge with every other node. So there's 4 nodes, 6 edges. So I've represented it in the top form here, which is clearly not planar because BD crosses AC, so therefore it's not planar. But I haven't proved it's not planar. In fact, that does have a planar representation, because if I picture I can picture sort of picking up the edge BD, that sort of string that crosses AC, stretching it up and over node A, and then sort of pulling A into the middle. And you can see I've got this other form, and that's still the same 4 nodes, the same 6 edges, but now it's a planar graph. So again, showing that I have a non-planar form doesn't prove that the graph is not planar. It just proves that I haven't drawn it in a planar way. Now, I put up 2 graphs here which are very clearly drawn to be non-planar, but whether or not a planar form exists for these 2, I haven't established that. I've just shown that here are two representations which are not planar. But in fact, these 2 are not planar, and they actually hold a special place in graph theory. The top one sometimes gets called the utility graph, which is the complete bipartite graph, where I have 6 nodes, and it's bipartite because here, as I've drawn it, every node on the left is connected to every node on the right, but none is joined within its own side. None of the left nodes share an edge, none of the right nodes share an edge. The bottom graph is the complete graph with 5 nodes. So sometimes called K5, the complete graph, 5 nodes, and the utility graph is sometimes called K33, a bipartite graph of 2 subsets of 3 nodes. So in fact, these graphs are non-planar, but in fact, they also have a particularly sort of powerful reach beyond themselves. The main way that we can show a graph to be non-planar is actually by relating it to one of these 2 graphs, K33, the utility graph, or K5, the complete graph with 5 nodes. And we show that if a graph contains a subgraph, which is one of these 2, then it's non-planar, or if it contains a subgraph which is a subdivision of either of these. Where a subdivision is just a graph formed where I add a new node to an edge. So if my original graph had the edge AB in, if I inserted the node X somewhere along the edge AB, then I've got one more node in the graph, and I've got 2 edges, AX and XB. So that's a little bit beyond the scope of this subject, but that's Kuratowski's theorem. So even once we've got this definition, actually spotting that I can find subgraphs which are one of these two, or that I can find subgraphs which are subdivisions of one of these two, is far, far from trivial. But I will end with a rare appearance of a mathematician who's not called Leonhard Euler. So proving that a graph is non-planar is not something that we will have to do in this subject. But in fact, we don't have anything else to do in this subject because that's the very end of the final video. So if you've stuck it out for the whole subject and you're right here, thank you for your attention.